Okay, so yeah, many survived. It's good to see. And the second thread, so I need to rush it a little bit, but I think I'll get to most of the things I wanted to say about the next two threads. The second thread, which I'll probably rush even more than the others, is the kind of perspective on this issue of small memory computation and randomness through graph connectivity and beyond. What more can you try to get? And it's natural to think about it in terms of graph connectivity. Specifically, directed connectivity captures the non-deterministic log space. Undirected connectivity is in RL. I mean, just a random walk by the result of Alunius et al. It defines essentially a class SL, symmetric log space, and is also known to be in deterministic log space. And we'll try to see what more can we do with respect to connectivity in small memory. So this is kind of going beyond just connectivity in terms of graphs. This result also led to some kind of oblivious. So I'm kind of separating between non-oblivious and oblivious de-randomization, where in non-oblivious, like in the Zagzoo, you look at the machine, you do things, and of course there are levels of that. In the pseudorandom generators, I think about it as oblivious de-randomization. You don't need to do anything, you just enumerate strings, you feed them to the machine, it's black box, and you check. So this result that undirected connectivity is in L translate to also some oblivious de-randomization. And this is what at the beginning we called pseudo-random walks, but then I recoined pseudo-converging walks. And I'll say what they are, but we can have them not only for undirected graphs, we can have them for consistently labeled a regular directed graph. And this is by also the work with Trevisan and Vadan. Okay, so what are these? First, what are these pseudo-converging walks? For example, for undirected graph, if you walk using a random walk on an undirected graph would converge to the uniform distribution or the stationary distribution pretty quickly. And if it's a regular graph, then the stationary distribution is actually uniform, which is similarly also when you look at regular directed graphs. So regular, I mean the in degree of each graph, of each node, and the out degree are all the same. It's all regular. And there too, in polynomial number of steps, you'll converge into the stationary distribution. Pseudo-converging walk is a walk that is not random, but based on some generator that produces some subset of walks. And its property is that it will also converge to the uniform distribution, or the stationary distribution if it's more generally, and it will converge in time which is polynomial in what it should have been. Perhaps it will be a little bit slower, but you will still converge to the uniform distribution. For example, for undirected graph, we can have these kind of walks that converge with the number of steps you need to 1 plus alpha. So just a little bit longer. And just to say what is this consistently labeled, when you have a directed graph, then you have the labels on, right? A graph, a walk is defined not only by the graph, but also by the labels on edges. So for example, this could be the fourth edge out of this node, and it's inconsistent if there is another node where the fourth neighbor is the same. So this is inconsistency, and or inconsistently labeled. And if for every number this is kind of a permutation, then it is consistently labeled. And I have this kind of graph, but I'll just say it out loud. We can understand the road between proving RL equals L and what we already know to be in L through graphs, both when you think about non-oblivious de-randomization and also when you think about oblivious de-randomization. For non-oblivious de-randomization, what we showed in RTV in the same work is that connectivity, proving RL is enough to look at connectivity for directed graphs with polynomial mixing time. So we know how to do it when it's undirected graphs. We know how to do it when it's regular directed graphs. And if we can avoid the regularity, then if we can do it without assuming regularity, but just assuming that the mixing time is polynomial, then we can show that RL equals L. In fact, we don't even need what we know here. We can actually extend it even beyond regularity. We know how to handle anything where we have some good handle of the probabilities of states. So this is with respect to non-oblivious. The gap lies in the question of regularity, for example. In terms of non-oblivious de-randomization, the gap lies in this consistently labeled. So we know how to do pseudo-converging walks for consistently labeled regular directed graphs. If we can do it without the assumption of consistently labeled, consistent labeling, if we have the same result without this assumption of consistent labeling, then we prove that RL equals L. On the other hand, kind of to give one open question, give a pseudo-converging walk for cliques. If you have a clique on n nodes, so every node is connected to every other node, I want a walk that would kind of converge to the uniform distribution, or even I think would cover everything. I think it's unknown, but I need to think about it a bit more. not making any assumption on the labeling. So for example, it could be that all the nodes have their first edge go to the same additional node. So without assuming anything about the labeling, it will be interesting to have a pseudo-converging walk for a graph which is as simple as a click. Definitely an expander, we also don't know. But the more recent thread I want to discuss is trying to get more than what you can get from pseudo-converging walks. So pseudo-converging walks are pseudo-random in the limit, or even after polynomial number of steps. After polynomial number of steps, you look like you took a random walk, because now you're in the stationary distribution. But there is still value in a pseudo-random walk. A pseudo-random walk will look like the right distribution at every step. If you take a pseudo-random walk and you look after 33 steps, you have the right distribution on the vertex that you are at. And that's something we don't know how to do. It's open and it's very interesting, even for undirected graphs. But in a recent line of research, there's progress about answering some of the things that could be answered if you add a pseudo-random walk. So what are these things? For example, things like heating times. How much time will it take you to reach from S to T? Commute time, escape probabilities. What's the probability you'll reach U before you reach V? All of those can be done if you had a pseudo-random walk, because you'll just run the pseudo-random walk and compute whatever property you want. But we don't know how to get a pseudo-random walk, but now we do know how to do it with small memory. And this is through the notion of Laplacian, because all of these things can be obtained by solving Laplacian systems of equation for undirected graphs. So the Laplacian of G is L, is a matrix L, which is D minus A, where A is the adjacency metric of the graph, and D is the diagonal degree matrix. Let's say if it's regular, it's the degree times the identity. If it's not, then you have the right degree on each location. And you want to solve systems of equations Lx equals B. For example, where L is the Laplacian of an undirected graph. Even that is already interesting. And I'll tell you a little bit about recent results, and then I'll move to the fourth thread. So Doron, Legal, and Tashma showed solvers in RL, in log space, in randomized log space. So at least it gives us the hope to de-randomize it and stay in log space. So the de-randomization works. And I work with Jack Mortag, a student of Salil at Harvard, with Sidford and Vadan. Give deterministic O tilde of log n space approximation of Laplacian solvers. So it's almost de-randomizing the randomized computation. And it helps us answer all of these natural questions. And there is a follow-up work that will say what it does. It can give us even more than that. And I want to tell you a little bit about the techniques, not too much, because I want to devote most of the time to the third thread that I want to talk about. But essentially, it should be thought of as a almost linear time meets small space de-randomization. So it's kind of combining two literatures and trying to see how they fit with each other. So there's been an amazing sequence of results on various graph computations, particularly Laplacian computations, in almost linear time. These are beautiful sequence of works, and we try to see which one of them can be used also for small memory, and how they fit together. They don't always fit as easily together as we want, but something can be done, and I'll tell you one thing towards that. And that's through this Peng-Spillman at least magical to me, formula for the pseudo-inverse of a Laplacian. So if this is the Laplacian of G, and I look at its pseudo-inverse, you have this formula that it is, I'll write it down and I'll show. Okay, so it's half times what's inside. And what is inside is the Laplacian of the complete graph, the clique, plus I plus the matrix that corresponds to G on both sides. And in between, there is the Laplacian, the pseudo-inverse of the Laplacian of the square of G. And now what you can do with this formula is try to apply it recursively. So now replace what you have here with the same formula for G squared. And you can do it logarithmic number of times. What you'll get at some point is the pseudo-inverse of the Laplacian of G to the 2 to the log n. But I mean, when you have order log n, then this would be approximated again by the clique, right? If you take an undirected graph, you look at its exponentiation n times, it's just like a random walk that takes polynomial time, and it converges to the uniform distribution. So this is approximated by the clique. So that's the hope. You're doing it again and again. You have lots of terms that are somehow manageable, and then eventually the need to do the pseudo-inverse disappears because you have a pseudo-inverse of something you understand very well. The problem is that all of these exponentiations would not be easy in terms of space. So the way we are combining the literature on small memory computation is by replacing the pseudo-inverse of G squared with the pseudo-inverse of a de-randomized square. So a notion that we had which corresponds very much to the INW generator, is of a pseudo of a de-randomized square. So a square of a graph corresponds to taking two random steps on the graph. A de-randomized square it corresponds to taking two related steps. So you de-randomize, you take a random step, but then you recycle the label that you're working on to get another step. Just like you're doing in INW, right? You take a step on X, and then a step on the extractor applied on X and R. And something similar to that, that was used by Rosenman and Vadan to give an alternative proof that undirected connectivity is in log space. And that's kind of our approach. I won't tell you too much about it because, as I said, I want to move forward. I'll just say that there is a follow-up work by the same set of authors from last year that goes further towards kind of approximating the behavior of walks exactly at R steps, which is something a pseudo-converging walk cannot do for you. For example, answering R-step conductance. Which is the probability that the rth step in a walk is not in a set S, conditioned on the fact that the first step is in S. In all of these works, the thing that we needed to do on the side of the de-randomization is to show stronger properties for things like the de-randomized square. If originally it was enough for us to say that the de-randomized square approximates the second eigenvalue, here we need to say that the de-randomized square behaves like the square for all eigenvalues. It's a good spectral approximation of it's a good spectral approximation of a square. So kind of the last thing I want to show you here is we want to say that for every vector V transpose the Laplacian of this de-randomized square of two graphs, G and H, times V. So for every V, this is approximated up to 1 plus minus epsilon, the V transpose, the Laplacian of G squared, V. So we have ways of de-randomizing a square that are very, very strong. Sorry?
All you need out of H is small second eigenvalue.
No, I'm saying that when we only cared about connectivity, all we cared about is second eigenvalue. We said, okay, you're squaring a graph, you're de-randomizedly squaring the graph, and you're making it more and more like an expander. For that, all we cared about was the second eigenvalue, but for using these kind of formulas, we need a spectral approximation, which is stronger. Okay, so I know that this was a bit rushed, but I hope that this means that I can be more leisurely with the third thread. Okay? Let's start with a new board altogether. So the final thread has two goals, which seem completely unrelated, but turn out to be connected. And I think there is an interesting lesson here about the value of good research or good theory and how good theory works. So we'll get to it. So what are the two goals that we want? One is a pseudorandom generator for constant width read once branching programs with seed that is even little o of log squared n. Or even better, that is close to log n. And I actually think that we are very close to obtaining this goal. We don't have it yet. We only have it for with 3. But I do think that if I'll get to the end, you'll be a bit more optimistic about it too. The second one is to look at a stronger model of computation that doesn't directly follow from the desire to de-randomize RL, to show that RL equals L. But it's otherwise highly motivated, which is generators, so PRGs, for read once branching programs with arbitrary order. So we have a branching program. The branching program reads one of the random bits at every step, just as we had before. And it's read once. It's not allowed to tell you again, oh, I want to see a bit I forgot from before. It's not allowed to do that. But what it is allowed to say is, I want the order of the bits to be x1, x100, x3. So I want the bits in this order. And I should say that this breaks Nissan's generator and other generators pretty easily. They're just not meant to do that. And the way I kind of describe, one of the main reasons I described them to begin with is just to emphasize how much they're using the order. So, okay, now you read these bits. I'm going to construct these bits that you read at the beginning. And now you're going to forget them. You only have a small memory on them. And I can recycle it and continue. And that would be fine. Why is it fine? It's fine because you're never going to look at bits from the first half again. And kind of the point that this was raised, and I'll mention the work, it kind of forced us. I mean, it's not only motivated and generalizes lots of objects that we like Epsilon Bias sequences, limited independence, that don't expect this particular order, but also it kind of forces us to develop new techniques. And it gives legitimacy to publish some papers that make progress when you have this requirement, but don't make progress otherwise. And it's hard to kind of convince the world, oh, look at my very, very interesting generator that uses square root n seed when you have a log squared n seed by Nissan. So the new techniques that are developed for this goal actually help us with this goal as well. So that's kind of my spiel about how theory works in mysterious ways. Okay. Now, sorry?
Is there a formal relationship between these two goals?
Not that I'm aware of. I also want to say that this here, we are emphasizing pseudorandom generators, and we're emphasizing them for a good reason. Because the problem of de-randomizing constant width branching programs is easy. If you have a constant width branching program, you can recursively approximate all the probabilities of every state, kind of one layer after the other, all the way till the end. And then you can actually approximate pretty well what's the probability from reaching from S to T. So that's not interesting. But what is interesting is the pseudorandom generator, and it generalizes, again, all these things that we like, starting with Epsilon Bias sequences and going up. Okay. So what do we know about constant width? Well, first, we have a good generator for width 2 branching programs. And this is by Sachs and Zuckerman, and there's a more recent view through Fourier analysis, but I'll tell you something about that because, yeah, I like it. So epsilon bias sequences full width 2. But it also, it kind of vice versa. A pseudorandom generator that fools width 2 is also epsilon bias, because linear tests can be computed in width 2. So why is this true? It's true because there are not a lot of things you can do in width 2, not a lot of layers that can happen. So if you have a branching program with 2 nodes, there could be nodes that do some linear computation, kind of take your state and XOR it with what you're reading now, XOR it with Xi, or ignore it. And the other things that can happen have the potential of losing information. The only other things that can happen are some kind of collisions. And a collision layer is one where for one of the labels, let's say for 1, the label 1, when you look at the 2 nodes in the previous layer and you take a step labeled 1, you reach the same node. What's nice about it? What's nice about it is that if you know that you took you did take a 1 at this point, then you can forget the entire history. You know exactly where you're going to be. You're going to be here. And now if we look not about one kind of layer like this, we look at the last logarithmic number of layers that have these kind of collisions, then we know that it is extremely likely that one of them will create a collision. So first, to begin with, we really don't care at all about the branching program that happens before the last logarithmic number of collisions. It will very rarely have an impact on you at all. Also, between these layers, what you have are just some kind of XORs, so a linear function. So essentially, in this kind of computation, all you care about is a logarithmic number of bits plus a logarithmic number of linear functions. And these altogether can have the right distribution under epsilon bias sequences. Okay. On the other hand, epsilon bias sequences do not, unfortunately, de-randomize with 3. And even very high independence doesn't de-randomize with 3. For example, if you look at all the sequences that sum up to 0 mod 3, they are epsilon biased with very good epsilon. And of course, with 3, we can identify that they sum up to 0 mod 3. Okay. So let me move to the other board and show you a little bit of the evolution of the research on constant width. And at some point, we'll kind of introduce this point about arbitrary order, and we'll see a revival and additional progress on this line. And really, the final thing I'm going to say would apply not only for constant width, but for polynomial width as well. which may be the most surprising part. Okay, so there's been quite a lot of work on special cases. Of constant width. Really a lot of beautiful results, which unfortunately I won't get into. But in special cases, I mean things like modular sums and regular branching programs and permutation branching programs. Lots of really beautiful pseudorandom generators for these kind of constructions. One thing I do want to refer to is a particular subset of these works, which give us one of the techniques that are really useful. What was the question? Okay. So it's the first the Braverman-Rao-Raz-Yudayev result I referred to before. Brody-Verbin, Steinberger, and Cohen-Ganor-Raz. And they show, well, first they show that these strange INW, kind of INW with very small, with large error, is actually useful for some of these branching programs, regular branching programs. But the interesting thing about this technique is also they tell us something about how errors accumulate in branching programs. And they don't accumulate as badly as they could have. They don't accumulate as a function of n. So for example, for regular branching programs, the kind of impacts that you can have only accumulate as a function of, let's say, log n to the width, something like this, very, very roughly. One interesting thing from this last result is that Santa-Vazirani sources, which I'll tell you what they are, with error that is reasonable, like 1/polylog, a full constant width branching programs. So what are Santa-Vazirani sources? These are sources, so you have bits, and the next bit is always a little bit unpredictable given the previous ones. So it's almost the property that I told you about INW with constant width. But for Santa-Vazirani sources, this happens always. No matter what the prefix is, the next bit will be a little bit unpredictable. And because kind of errors cannot accumulate too much, this is good enough. So this kind of begs the hope that INW with large error with error 1/polylog would work for constant width, and I think it doesn't. So, okay. Then, okay, good. I'm gaining some ground. Then I want to talk about a different kind of generator, and that would be the connection that we have to this arbitrary order. Really a very, very different approach now towards constructing generators in this arena. So this is a work with Gopalan, Mecca, Trevisan, and Vadan. And this gave a seed, which is O tilde log n/epsilon, that fool a bunch of creatures that are special cases of constant width. So they fool combinatorial rectangles, read one CNF, And they also give heating set generator for with 3 branching program. The major part of all of this, the improvement is for the dependence on epsilon. So there were creatures that gave kind of seed which is quasi-logarithmic, but only with high error. So you can have error which is 1 over poly and get a seed which is pretty strong. But the point is that this generator is very different than INW. And in particular, it does apply to arbitrary order of the bits. And this generator rely on what we refer to as mild pseudorandom restrictions. And in that, it extends a paradigm of I-type Victor zone. It directly relies on pseudorandom generators that directly influence from pseudorandom generators for hashing in the work of Celis, work with Celis, Segev, and Vider. So what's this idea of pseudorandom restrictions? We know pseudorandom restriction. We love pseudorandom restrictions for many, many reasons. They tell us something about the power of various kind of computation objects, but they can also be used to construct pseudorandom generators. Instead of being just a thought experiment, they can be used as a pseudorandom generator, where the idea is that you select a subset of the bits, you plug something into them, for example, epsilon bias, and then you, again, select a subset of the remaining bits, and you plug something into them, let's say another epsilon bias, and you continue this way. This gives you a generator and this is essentially exactly this generator that we're going to talk about, that in particular does not rely on the order of bits, because what you have at every level is epsilon bias, and epsilon bias is epsilon bias regardless of how you read it. Okay. So I want to tell you a little bit about kind of the kind of shift that is needed to make I-type Victor zone approach applicable in this context, because as it was, it just doesn't work, and you need a slight shift in the way you think about it. So let's look at these pseudorandom restrictions. So let's assume you have a function f, and it depends on 2 inputs, x and y. Now I draw them as if it's first the bits of x and then the bits of y. You should think about them being mixed. Kind of this is a random selection or pseudo-random selection. So you have f is f of x, y. And what's the AW approach? If for almost all x, the function that you get by hardwiring x is simple. So if fx, which is now only a function of y, and is defined to be fxy, is simple, for example, if it is fooled by epsilon bias, then what we can do to create a generator that fools F is first just use a generator to replace Y. So you have a generator that creates something, for example, an epsilon bias sequence, and you know that when X is uniform, then, or for most X, this function is simple enough that epsilon bias would fool it. And now you can continue recursively. Now that you already set Y, you can look at X and de-randomize X in the same way. Because usually these objects, when you hardwire Y, now will be a smaller version of X, of F. So let's try to do it and again, as I said, X, Y are, you should think about them as selected uniformly, or the locations are selected uniformly or pseudo-randomly. So let's try to apply this. I mean, it's very appealing. Let's try to apply it even for a simple F, which is a read one CNF. Let's make it even easier and just make it into a tribe. Let's just think about tribes. So if f of x is x1 and x2 up to xl, or xl plus 1 up to x2l, or and so on. So we are dividing two tribes, and we're asking, is there a tribe where all the members said 1? Is there, right? And we need to set L to be roughly log n, so this tribe is balanced. Half of the time it's 1, half of the time it's 0. So let's try to apply this. It actually can work. It can work for this. If you set everything, if you set all but 1 over log n of the bits randomly, most of the time after you set them, you're left with something very simple. Most of the tribes will either disappear completely. A constant fraction of the tribes would disappear completely. Even those that do not disappear, many of them will just have somebody already saying 0, and therefore we can ignore them. You'll be left with something that depends on very few. I mean, depends on how you set it. You can be left with something that's constant, or if you set the parameters differently, you'll be left with something that depends on a few variables. So that's great. You can do that. And you can do it even pseudo-randomly. Choose the log n bits to keep alive, let's say using some epsilon bias, fix all the rest with epsilon bias, and continue. The problem is that when you fix a tiny fraction of the bits, just 1 over log n, you need to repeat it. In order to fix everything, you need to do it log squared n times. Each time you're investing log n bits, meaning that you got a pseudorandom generator with seed log to the 3n. So it doesn't look very appealing because we have a log squared n seed. You can optimize and somehow get there log n log n seed if you think a bit harder about it. But you're no better than the Nissen's generator. So it looks, yeah? Excellent. Thank you.
Even though it doesn't work, or it's not very
Right.
just spell it out
Right.
carefully. What exactly?
So let's,
You're starting with tribes.
Right.
And how do you build a pseudorandom generator?
right. So let's say, so how does this pseudorandom generator work in general, this approach? You select a subset of the bits, which are the bits you're going to de-randomize at this point. So here you're going to select just logarithmic fraction of the bits, and these are the ones you're going to select to de-randomize. So the generator will tell you, and let me, you know what, I have this for kind of a little bit later, so let me just, I'm really very close by. So let me just write how this generator works. So this generator kind of combines two kind of sequences. Sequences which are, let's say, the epsilon bias that you want for the de-randomization, and an epsilon bias which is a selection. So let's say you have this y0 and t0. Y0 is epsilon bias, and T0 is eventually we'll want it to be epsilon bias too, but now think about it as a random kind of sequence of locations. So let's say here you have yi 0, and here you have yj0. And now we're kind of summing these up. We can have two things. If this is 0, then this means that in the sequence we currently have, this is a star. We don't know what the value that we put here. If it is a 1, then the value we put here is yj0. So we have a selection sequence that tells you out of an epsilon bias sequence which ones you select, which one you not. The next stage, you're going to put another selection. So you'll put another y1, t1, and you'll do the same, but now you'll only concentrate on the stars, because these are already fixed. So this is the procedure you want to do. Let's see what happens here. So you select 1/log n bits, which we're going to fill in with epsilon bias. To say that this works, to convince you that this works, I need to tell you that when you fix everything but this 1/log n, using a uniform string, then what I get is a very simple creature. And this very simple creature would be fooled by epsilon bias. And for this creature, for the tribes, if you fill almost everything with uniform strings, you only leave alive 1/log n of the bits, and the rest you put randomly. And what happens is that most of the tribes completely disappear, and you're left depending on very few bits. And if you take a larger order for the log n, it will very surely be already fixed at this point. There may be a tribe that already said yes, and perhaps all the other, or perhaps all the tribes have somebody who said no. Okay? So therefore, you're left with something very simple that can be de-randomized with epsilon bias. But now when you do that, with this spaced, then this story that I'm telling you will take a long time, because I only fixed here 1/log n of the bits. Now in the second part, I'm going to fix 1/log n of the remaining bits, and so on. To fix everything, I need to do it log squared n times. And in fact, if you just want, let's say, the mild pseudorandom restrictions, you want at the first round already to fix half of the bits, then this doesn't seem to work. because a tribe, after you fix half of the creatures of a tribe randomly, let's say you select half of the bits of a tribe, you set them uniformly, most likely what you got is a tribe which is a little bit smaller, a tribe of size square root n instead of a tribe of size n. This is not really simple enough to de-randomize with epsilon bias. So that's why this approach seems to be doomed. If you have more...
If you're setting the bits randomly to 0 or 1, don't you kill most of the tribes by setting one to 0?
So now I'm setting half of the bits randomly.
Yeah.
So I will only be left with square root n of the tribes.
Okay.
That would be alive. These are all the tribes that the half of the bits that I set are ones.
Yes. Okay.
And so, but it's still a big, pretty large tribe.
Okay.
So I shouldn't succeed. And okay, so what's the catch? What can we do? The catch is it's not, I mean, an amazing idea, but it's a powerful idea. The powerful idea is to say, okay, when you're saying I'm going to fix half of the bits at random, and then hopefully I'm left with something very simple, you already lost a lot of the power of this random restriction. A lot of the power of the random restriction is when you don't fix the bits at random, you keep them alive but random. So let me kind of just write it down. What you really want to de-randomize is not fx, not this function where you fixed, let's say, half of the bits at random to be x, but instead you want to fool the bias function. Which is the expectation over the uniform distribution of f, where you're setting half of the bits to be uniform. You're not fixing them to x, but you're setting them to be uniform. So the bias of this function, each one of these functions, for every particular fixing, for some of them, this function will be fixed to 1. For others, it will be fixed to 0, perhaps. For some of them, it will be 2/3, 1/3. But there will be some kind of so this is a function of this variable, and this is what you want to fool. So what you want to fool is not most of the restricted functions, but you want to fool the function when the restricted variables are left alive, are uniform. Let's try to look at that here for the tribes. So as we said, one of the variants is that I'm selecting half of the bits here, I'm fixing them at random, and I'm left with a smaller tribe. I'm not happy with this one, because a smaller tribe is still a tribe, it's still something that's hard to de-randomize. Instead, let's imagine that we're looking at this tribe. And now this tribe, again, is a function of f, but some uniform strings, and x. And now, for example, in the first tribe, you have u1 and x2 and u3 and u4 and x5. So some of the bits are uniform, and some of the bits are x. The second tribe, again, you have some of the bits are uniform, some of them are x. I want to say that this function, when these are uniform and are staying alive, is a very simple function. And the reason is that all I want from x's here, because u remains uniform, all I want from the x's are that they will mostly kind of on average behave in the right way. What does it mean? that they will leave. I mean, the X's themselves can kill some of the tribes, right? So if x2 is 0, then this tribe is dead. It will never be all 1. But if all the X's are 1, I still have a tribe which is alive. So what I want is that the number of tribes where every X is 1, this number of tribes is distributed with the right distribution. It is distributed with the same distribution as if I placed here uniform values for the X. And this is something that's much, much simpler. In fact, this is something where epsilon bias or order log n wise independence would do the trick.
So say the condition again, number of tribes.
So let's imagine that every tribe sees half of the bits that are uniform, and half of the bits are these X's. Now, for some of the X's that I put in, the tribe would disappear because one of the X's is 0. So I only care about the number of tribes that leave after I select the X's. These tribes that are left are those where all the X's are 1. So I have roughly n tribes. Each one of them has log n over 2 or L over 2 values of the X's. In expectation, the number of tribes that are supposed to survive in expectation is n over 2 to the L. Because for all the X's to be 1, this has to happen with probability 2 to the L over 2. Because there are only L over 2 values of X's. So this happens in expectation. I actually want it not only in expectation, I want the right distribution. So I want the probability that this number of tribes will survive is what it should be. Probability that one more tribe survives or one less tribe survives. They're all the right distributions. But even just think about the expectation. I want it to be that in expectation, this is the number of tribes that survive. So perhaps I'll move forward just to tell you some of the results that have been in this area, but kind of this is where the AW approach was stuck, and this is how we kind of make it work forward. So we don't think about fixing the values of the uniform choices, but keeping them alive. In this picture, we're not thinking about what happens when X is fixed. We're thinking what happens when X is set to be uniform. When it's fixed, it simplifies some of the function, but when it's uniform, it really mixes things much more. Okay, so let me, since I really overestimated my time, which sounded infinite when I started preparing that. Let me tell you a little bit about the results. And I don't think that I'll even mention all the results I wanted to mention, but I think at least I'll give you some flavor and some source of optimism. Right. So one thing is that this kind of a construction that kind of combines lots of epsilon biases in various ways. So you take this to select some of the bits, and then take another selection of some additional bits. This is only depending, kind of composing epsilon bias sequences is always order independent. So you get a pseudorandom generator that's very, very different than the INW generator. And right, very different than the INW generator. In particular, works in all orders, which makes me move to this result that I kind of give a lot of credit in this area of Impagliazzo, Mecca, and Zuckerman, which raised this question. They asked, OK, what can you do when you need to deal with every order of computation? And they showed that you have a generator with seed NW to the half plus little o of 1. That fools width W, length N, read once branching programs, which is, of course, much, much worse than Nissan generator. But it gives you something that Nissan generator doesn't give. So given this result, I'll show you lots of papers that nobody would have accepted without this line of research that kind of got us closer to things we like. So a result with Steinke and Vadan. Kind of introduced some of the Fourier techniques that have been used in this area. It also gave seed order of W squared log squared N for permutation branching programs. So for permutation branching programs with constant width, it gives you seed which is log squared N. Lots of other results that I'll skip. Steinke-Vadan and one showed arbitrary width 3. So not permutation branching program with seed which is O tilde of log, which is 3n. The work of Ishan, Atami, myself, and Tal from 18 showed that you can reach any constant width branching program with seed that is O tilde of log n to the W plus 1 with arbitrary order. So again, this is again a result that makes no sense if you ignore the order. And then I want to, I skipped lots of results and I apologize to the authors. But to mention kind of two of the more recent results. One is a result with Mecca and Tal. Which relies on this line of research, but actually works for ordered branching programs, but gives width 3. So seed O tilde of log n for width 3 branching program. So arbitrary width 3 with seed which is O tilde of log n. Again, this is kind of the first progress over Nissan's generator. And this is what I mentioned at the beginning, but we don't know width 4. So, and yeah, OK. And a result of Forbes and Kelly which gives for arbitrary order, so arbitrary order, seed order log cube and for polynomial width and seed O tilde log squared n for constant widths. So for constant width, it improves this result by giving you polylog, but it doesn't depend on W, or this doesn't depend in the exponent. But the interesting thing is that it also works for polynomial width. So this is an alternative for Nissan generator that works for every order, essentially with this kind of mild restrictions. And yeah, completely different, but still has polylog seed. I want to say one thing about the Cayley-Forbes result, and I'm almost out of time. But I want to say that this kind of an approach, to make it give you seed which is O or O tilde of log n, you need two steps. So step one is to show that a kind of a mild pseudo-random restriction work. So that if you fix half of the bits, let's say with an epsilon bias sequence, and the choice of the bits is also, let's say, with an epsilon bias sequence, then this fools the bias function. This is one thing you need. And step two is that, let's say, log n applications of step one are sufficient. So what do I mean? After you fix half of the bits, and then you fix half of the bits, and then you fix half of the bits, you need to do it log n times to fix everything. So if you're investing log n bits in each time you do this restriction, and you do it log n times, you still have a seed which is log squared. So somehow you need to argue that doing it log n times is sufficient. This was true, for example, when we looked at read one CNFs. It was true in other contexts, but you need to do it in general for any model for which you want to do it. And at this point, for constant width branching programs, so for constant width, we know by Forbes-Kelly that this part works. So constant width branching programs, a mild pseudo-random restriction works. If you choose half of the bits with an epsilon bias sequence and you select them to be epsilon bias and the rest are uniform, this is a generator for constant width branching programs. So all that's remained to de-randomize constant width is to show the next part. That after you do it log n times, which means that you fix all but a log n fraction of the bits, the remaining are simple. They can be fixed with, let's say, epsilon bias. This part requires more work, but I was hoping to have a surprise announcement by some of the people in the audience, or so it's still not here, but next time I'll give this survey. Okay, thank you.